start with Kobe doing spectacle lens design.
Thank you. Okay, I think I want to start with a follow-up on what Marcus told us yesterday about the experience of writing papers with Joe. I had a similar experience. I would write the first draft, give it to Joe. I get it back the following day with zillions of corrections and remarks and changes. The first I was happy about it because it was a free education. Then I realized I don't improve. I mean, months goes by, other months, and I still get zillions of corrections about every draft I write. Then one morning, I go into the office, Joe comes in, and again gives me a draft with many, many corrections. Now I was surprised. I told Joe, you know, you wrote this draft. So he said, okay. Who said my draft cannot be improved? So the lesson is that it's not that you wrote bad English or bad something, that every draft can be improved. That's my lesson. Okay, I talk about spectacle lens design. This is very different than other talks here because this is commercial, not or industrial project, not an academic project. So, first of all, spectacle lens design went through major evolution in the last few decades. The main reason was a need. I see many people in the audience who use multifocal or focal progressive lenses. This became there's huge demand for them. The initial design 30, 40 years ago were very poor. So this need from the public created a revolution in the field. This evolution has been helpful in designing other specialty lenses, like sport lenses. Also, there were major breakthroughs in manufacturing techniques. It's another reason for the changes in the industry. This is a unique sub-discipline in optical design because, first of all, the eye is generally not a symmetric optical element, so it needs an asymmetric correction. Second, the eye keeps moving, so we scan the optical field in many, many directions, and we want to optimize vision in all these directions. But on the from the other point of view, the pupil is relatively small, so you need only a small part of the wavefront entering the eye to get a good design. Now, therefore, for almost all practical purposes, you only need the quadratic part of the incoming wavefront. So a typical design, now how do I operate this? Oops. So a typical design consists of three numbers. There are sphere, cylinder, and axis. This is really a bad way to write down a 2x2 symmetric matrix. Well, so we get a prescription for each eye, they give you a 2x2 symmetric matrix, which is the quadratic form of that you want the incoming wavefront to have, so you'll have good vision. So the goal of the design is to have a spectacle. It will convert whatever comes into the eye into this symmetric, into this quadratic form in every different gaze direction, which is essentially impossible. Now, where the need comes from, the eye is an autofocus optical element, so when you look at a nearby object, it accommodates. However, this ability is lost when we reach the age of 45, gradually, and it's getting worse and worse. But we still maintain another dynamical property, which is convergence. We look at a nearby object, the eyes move toward the nose. So the idea behind progressive or multifocal lenses is to use this dynamical ability, the convergence, to overcome the loss of accommodation. So the optical power changes in the nasal direction. When the eye goes down, in my spectacle, when the eye moves toward the nose, the optical power increases to compensate for the loss of my accommodation and ability. So we want to have a design that will give essentially far vision in the forward direction and increasing design when you move toward the nose. But should give good vision in all possible gaze directions. This is a schematic picture. You see the lens and the eye. There are many, many objects. Each object emits essentially a spherical wave. It is refracted by the lens, and after refraction, you want to achieve the shape given by this dioptic matrix that I showed before. That's the goal. So we are faced with the following equation. To build a design code, that will give a very good focusing for many points, objects in many directions, to prevent distortion in the visual field for extended objects. Very fast code. The designer is working, doesn't have time to spend an hour till getting design for a new customer or a new brand. There are many other factors. I'm not going to tell you all the secrets of the trade. Many other factors. Cosmetic is a huge, or vanity is a huge factor in the industry. Lens must be very thin. Nobody otherwise would buy it. So this was where we were when the project started. But we knew three things. First of all, we worked on this problem in the past earlier for some company, and our earlier model was based on a very good approximation of the optics. And even this good approximation led to very difficult mathematics. The underlying Lagrange Lagrange equation for the functional we optimized was a highly nonlinear version of the biharmonic equation. Very nasty mathematics. To solve it, by the way, we needed finite elements that we copied from Boeing. That's the element Boeing used to design the 747 wing. So we knew it's going to be difficult mathematics here. Okay. Second thing we knew is that we should forget everything about optical design. Standard optical design is useless here because of the eye is not symmetric and you need many gaze directions, etc. But we knew, and also this, as I said, this is a commercial project. This was invited by some Israeli company, and the goal was very simple: to design a better lens than the leading lens on the market. We had two lenses that were considered to be the best on the market. You should do something better. That was the goal. There was no way to, no place to play games here. But we knew one more thing. We knew from our previous experience what is the tool. So I'm going to speak only about one block in the design, which is the main tool we use to analyze the lens. So in the optimization process, you first have to say what is the quality of the lens in any given gaze direction, and then optimize about it. So you need a tool to analyze optically correctly the vision in every gaze direction. And the tool was introduced by us many, many years ago by Hamilton. This is Hamilton's first paper, which he introduced is point iconal function. He gives another name. By the way, notice this paper was published in 1822, but it was submitted in 1824. Why this is significant? In 1824, when it was submitted, Hamilton was a 19 years old first-year undergrad student at Dublin. When it was published, 4 years later, he was professor of astronomy in Dublin. So it took him 4 years to change his title. Now, Hamilton correctly stated that this characteristic of point iconal function captures everything you want to know about the optical system. And what he meant by this. So the function is this. You have a plane, xy plane, I call it P, on one side of the optical element, another plane, P prime, with coordinate x prime and y prime on the other side of the optical element. And there are many ways going between the two planes. So the point iconal function is a function of S, a function of 4 variables. It is the optical distance of going between the point xy on one plane to x prime, y prime on the other plane. That's the function, a function of 4 variables. And indeed, it has everything. It gives you everything you want to know about optics. For example, suppose you want to go from a fixed point xy to x prime, y prime on the other side. Which direction you should go from? The direction is this gradient at the bottom. So you can deduce for this function anything you want. Moreover, Hamilton pointed out in a subsequent paper that the other iconal function, like Sm, which is called point angle function, which is a Legendre transform of the original point iconal function. Now, this is the foundation of his work on geometrical optics, but it was not being used in optical design. So first, it's a function of 4 variables, very difficult to compute, and even if you can compute it, then what do you do with it? It's not known, for example, given such a function, how to realize an optical system. It's a totally open problem. The famous mathematician Karl Theodori, who worked in Berlin 100 years ago, he was one of the founders of set theory and logic, also worked on this problem, how to realize a given iconal function. He couldn't solve it, and he claimed it is the hardest problem he worked on, much harder than logic and set theory. So it was never being used. But what we realize is that it can't be used in our context, because what we really need is only a small part of the wavefront. Don't need the entire function. So, which means practically, if I take a certain given gaze direction, and look at this direction, and I expand the point iconal function about this direction, the linear terms vanish by symmetry, and we are left with the quadratic terms. With this, given by this matrix S, this 4x4 matrix with 4 2x2 submatrices with some symmetries. And so this matrix S is an approximation of the local behavior of the point iconal function in every gaze direction. And what we realized is that this function contains everything we need for optometry, for lens design. This is the picture of the base ray, given direction, and the expansion about it. So, for example, the direction. If I know this matrix and I get 2 points, I can find the direction of the rays connecting these 2 points. This is an example of an application. So, okay, as you see here, there are 4 submatrices. The submatrix R, which is the matrix submatrix, is essentially our original dioptric matrix. If I can control this submatrix R, I can control the prescription. That's one good news about this function. Another one is the submatrix Q. So Q appears twice in this 4x4 matrix. So the submatrix Q controls magnification and distortion. For example, if I look at from a point object from a point with the eye into an extended object in some direction, there is a lens between them. It looks different direction, and the difference in the direction is given by the matrix Q times the distance to the object divided by the refraction index. So this matrix Q contains information about extended objects. So we need to focus object on the retina. This is done by the R matrix, and to control extended objects. Q is not symmetric, so you can write it as a rotation matrix times a symmetric matrix, and therefore there are 4 parameters. One is the average of the eigenvalues of the matrix epsilon. One is which is the magnification. The difference is the distortion, and there are 2 angles: the magnification angle and the torsion angle. So these 4 parameters characterize extended objects. So if you know this matrix, this Q and R, or the 4x4 matrix in every gaze direction, we can characterize a given lens. So how to find it? How to compute it? It must be done extremely fast. Our experience is that if a designer, so our experience is this: if you write a design code for optical engineers in this context, the code must give you a lens either under 10 seconds or more than 15 minutes. Under 10 seconds, if the designer wants it, gets the answer, is very happy. More than 15 minutes, you want to code, and the code runs, you go to make some coffee, talk to some people, do other things. In between, you get nervous, is unhappy about it. So clearly, the goal was here to do it in under 10 seconds, very, very fast. Now, there's no way to compute the point iconal function itself. It turned out to be extremely hard. We tried to do it, but in every gaze direction, it was very hard. So we found a way to overcome it. And the way to overcome it is to consider the other iconal functions and also the transfer function. Given the point x, y in direction of a ray xi eta in the first plane, find the point and the direction on the other plane, the other side. This is called the lens transfer function. This function can also be linearized. This is its linearization, and there are again 4 2x2 matrices that characterize the linearization of the transfer matrix. And if I know how to find A, B, C, and D, I can invert the linear equations and find my original R and Q, which is what I really need. And this turned out to be easier to compute. So how do you compute them? So you start at the point object, say, and then you move the observation plane. Just moving the plane or propagating the function in free space is easy. Here is the transformation. The hard part is when you reach a refractive surface. How to compute it beyond the refractive surface. But after all, this is a local approximation. So we found how to do it. So Z represents the refractive surface at a given point where the base ray gaze direction intersects the lens. And I and I prime are the angles made by the incoming and outgoing base ray at that point with the normal to the lens surface. And N and N prime is the refraction indices. So the equation for A, B, C, and D are what see beyond Snell's law. This is beyond Snell's law for the quadratic part of the waveform, not just for the linear part, which is the classical Snell's law. This is the heart of the computation. This formula, it tells you how to compute the length transfer or the point iconal beyond a given refractive surface. Now, the advantage of how to get it, well, you solve basically, you either solve the iconal equation, or in this case, you could solve it geometrically using the interpretation of Hamilton's iconal functions. Fine. The advantage of doing this is that a transformation can be done step by step. So, so what we do, we start from an identity near the point object, then you propagate to the first length surface, then you refract. Then you propagate it again to the inner length surface, refract again, then go to the eye. And each step here could be done by the method I just showed. And then once we complete all the refraction and transfer, we can invert it and get what we want, our 4x4 symmetric matrix, which contains all the information in a given gauge direction, and we do it over all gauge directions. And it turned out that this was a very fast way of calculating a lens performance, and then we optimized over the entire lens. A very big commercial code is written above this formula. So we finished. But see, this was a commercial project. We didn't start looking at the literature before we started. We looked at some basic books. Nobody told us what to do here. So we did everything by ourselves. Then we thought, wait a minute. There was nothing we did here that could not have been done by Hamilton. Nothing. So we went back to look at Hamilton's papers. So I searched among his papers. They're very lengthy papers. I couldn't find it. He just didn't bother to do it. Did somebody else did it? Well, the answer is yes. This somebody else is Maxwell. So 1874, sorry for the bad photocopy. So in 1874, Maxwell wrote a little forgotten paper, but essentially in different notation and terminology, doing the same thing, but only for lenses with radial symmetry. That was his limitation. So I was happy to see that Maxwell, and it's only by Maxwell. Then I showed it to Joe. So Joe, you know, we did this calculation, and Maxwell did it before us. Joe said, wait a minute, I also did it. So
What was before him?
actually, this is Keller squared. Joe and Herb Keller submitted in '49, and in this paper they worked did this transfer computation for a general surface, not necessarily radially symmetric, but only for the R matrix that I showed in the beginning. And in fact, for almost all optometric reasons, you don't need the R matrix. I can tell you a secret, almost nobody is using this Q matrix. So in fact, this calculation was done by the Keller brothers already many years before us. But it's okay to be screwed by them. And also, fortunately for our patent, none of them did the full case. So in fact, our patent had no prior art to invalidate them. Okay, I summarize. So we saw that the Hamilton point iconal function, or actually it's 4x4 quadratic form, is a very useful tool in designing spectacle lens. And it was, in fact, computed by Maxwell in the radial case, and by Keller and Keller in part for the general case. And what we discovered later, also Walter, Dutch physicist, did something similar in the general case, just like we did. If you don't work with Gershon Molansky, the Technion, that this formula is a central part in a large commercial code. This code was implemented by an Israeli lens manufacturer. Now, is it successful? Now, this is a consumer product. So you can compare, and the comparison, there's no jokes here. People buy all the brands in the market and compare them one by one with different niches in the market. So at least until I didn't follow it in the last 6-7 years, but when I still follow the market here, the lenses based on this code were typically the top lenses in every category. And in fact, I know that now almost everybody is following this kind of approach, although they don't say it, because they don't want to be sued for infringing patents. For me, it was a very interesting lesson in how the real world works. For example, people steal technologies, people have hard time understanding what you do. You have to write the code in a reasonable way. The main lessons here, which is a subject for a different talk. But I'll end up with a picture of Joe, which I found in my album, a very old picture, which I found, which I don't think was ever published before. Not very good quality. This picture was taken in a Passover night dinner at my home in Palo Alto in '87. So you can see next to Joe is Dan Givoli. That's how he used to look. And next to him is Peter Sternberg. That's how he used to look. And I have no idea who the other two guys are. And what struck me in this picture was the head cover that Joe is using. I asked him, where did you get it? He said, well, this was used by his grandfather in Russia. And somehow it went down the family line. Eventually he got it, and he used it on a very special occasion, like this special event. So I'll end up here. Thank you.
Time for one question.
Yeah.
I noticed you factored out a rotation matrix. So does your method relate to various standard numerical analysis concepts, like singular value decomposition? Or is it quite unrelated?
Let us say the question.
You know, in numerical analysis, there are various decompositions of matrices.
Yes.
And one of the fundamental decompositions is a singular value decomposition.
Ah, yeah,
I just wondered if that's an irrelevant
we did not need it.
You didn't need it.
It's a 4x4 matrix, and you can say anything you want about it without using heavy machinery.
You don't need any of that
No,
stuff
no,
at
no,
all.
we don't
Very
need it.
interesting. Yeah.
Okay.
Yeah.
Time for another question.
Okay, thank you very much.